and welcome to NASA Science Live. Today we're discussing important science around Earth's icy regions and how it can impact those living in warmer regions around our planet. You might have heard in the news that enough ice has melted from Antarctica and Greenland to rise sea levels about half an inch over the past 16 years. We have the scientists behind that NASA study to talk to us more about what we've learned and what it means for our planet. We'll also take you to the coast of Virginia to see the real-world impacts of Earth's melting ice. Before we get started, let's take a step back and learn about the cryosphere. That's the frozen water parts on Earth's system.
Here at the end of the Earth, it still feels like a place for raw exploration and adventure. It's vast in all directions and ground zero for some of the biggest questions we have about the climate. But when we decided to make a show about the frozen places on Earth, we knew there would be one hurdle we would need to jump over first. What is the cryosphere?
The what?
Ooh.
I have no idea.
While I'm aware of the cryosphere, I don't actually know what it is.
It has something to do with ice. All right, that's all I got.
How do you get people acquainted with the cryosphere when most of us don't even know what it is?
Hey, so here we are in Washington, D.C., standing on the roof of NASA headquarters. That's the Capitol building right behind me. And what headquarters does is kind of serve as the focal point to connect the dots. The cryosphere is everything from the snow that falls by your house to the icy reaches of the Himalayas, to the big ice sheets of Antarctica all the way at the South Pole, and also the frozen ground of the Arctic, and even some of that frozen ground that's currently under the ocean.
If you had to break it down, you'd have a mix of sea ice, snow cover, permafrost, ice sheets, and glaciers.
Right now, our best predictions are that sea levels will rise anywhere from 1 to 3 feet within the next 100 years. 3 feet of sea level rise has the potential to displace about 100 million people, which is a lot of people that need to find new homes.
Our current reality places us at a near tipping point, and the cryosphere is playing a huge part in that delicate balance.
So one of the things people don't know about NASA is that we study the Earth, and we've been doing that since NASA's inception back in the 1950s. And we study the frozen part of the Earth in a variety of ways.
Missions like SNOW-X, Airborne Snow Observatory, Oceans Melting Greenland, Operation Icebridge, Arctic Boreal Vulnerability Experiment, and countless other labs and individual researchers stand at the forefront of monitoring the cryosphere. We're taking you with us as we follow NASA explorers on their journey to the frozen ends of the Earth as they study our rapidly changing world from satellites, planes, and boots on the ground.
Wow, so it sounds like the cryosphere is a place we all depend on, but many of us will never go to. I'm joined today by Alex Gardner, NASA glaciologist. Alex, can you tell us more about why NASA studies Earth's ice?
Yeah, absolutely. NASA studies Earth's ice because it's incredibly important for the rest of the Earth system. The poles cover a large region of the Earth, and they interact with the Earth system in ways that cause large global changes. The melting of the ice sheets are responsible for changes in sea level rise. The formation of sea ice drives the thermal haline circulation, or the circulation of the ocean. Changes in snow cover year to year cause large changes in the Earth's energy budget. And so if we want to understand the Earth, we need to understand the poles.
So how does NASA study Earth's icy regions?
Yeah, great question. There's a lot of different ways that NASA studies the polar regions. And NASA is really well equipped to do this because these are very harsh environments that are dark for up to 6 months of the year. And so NASA has a suite of satellites and airborne missions that are designed to study the polar regions. We have a satellite that launched in 2018, ICESat-2, that's a very advanced laser altimeter that counts individual photons that bounce off of the Earth to measure height changes. We have another satellite that launched in 2018, the GRACE follow-on mission. And this is a fascinating mission that's able to actually measure subtle changes in the Earth's gravity. So as the ice sheets grow or shrink, we can actually see gravity change in response to those changes. And we also have the airborne missions. So we have a mission called the Oceans Melting Greenland that surveys the periphery of the Greenland ice sheet to measure changes in oceans and see how that's impacting the ice sheet.
What are some of the discoveries that your colleagues have been making about these regions?
Yeah, so it wasn't very long ago, only a few decades ago, we assumed that the ice sheets would respond fairly slowly to changes in climate. And what we've discovered over the last few decades is that's far from the truth. There are all these really interesting feedbacks that occur that cause the ice sheets to respond much more rapidly than we had anticipated. So the oceans are able to eat away at the edge of the ice sheets very quickly, which causes the ice to flow more rapidly into the ocean. We've discovered that water from the surface can easily reach the bed of the glacier, raising the pressure at the bed of the glacier and reducing the friction that causes it that resists the flow into the ocean. And in some places, we've discovered that the geometry of the bed of the glacier can cause glaciers to retreat irreversibly once they start to retreat. And so there's these large one-way feedbacks in some places that can cause rapid changes in sea level rise.
It is such an interesting region. We've got some questions from social media. So we have on Twitter, Rut13 asks, what kind of information can we get from ice and how can that information be useful to us?
Yeah, so there's lots of different information we can get. Some of the most interesting information is actually coming from ice cores that give us these long, detailed records of Earth's climate history, because it actually traps little pockets of air in the ice cores. NASA's not collecting the ice cores, but what we are measuring is the changes in the ice sheets. And so what we can see is if we warm the temperature of the ocean by 1 or 2 degrees, what does that mean for how quickly the ice shelves melt? And if we generate water on the surface of the ice sheets, what does that mean for how fast that they can slide into the ocean? And so it's really about developing understanding so that we can provide projections into the future of what the response to future changes will be.
Wow, that's fascinating. So thank you so much for this insight, Alex. As we mentioned at the beginning of the show, NASA has just released brand new science results about accelerated ice melt. Let's take a look about some of those details about how Earth's ice is changing.
Using the most advanced Earth-observing laser instrument NASA has ever flown in space, scientists have made precise, detailed measurements of how the elevation of ice sheets in Greenland and Antarctica have changed over 16 years.
We can actually see some processes at a scale that's almost long enough to tell us about the climate in those two places.
Scientists took ice sheet elevation measurements from 2003, overlaid data from 2019, and analyzed where the data sets intersected in order to see where ice was lost or gained. For example, the study definitively shows that the East Antarctic ice sheet, the largest of all the ice sheets, is growing.
But more importantly, what we find is that growing is more than offset by increased losses coming from the West Antarctic ice sheet, which is thinning very rapidly as it responds to warmer ocean temperatures, specifically in the Amundsen Sea embayment area.
The West Antarctic side, we're seeing strong thinning on the ice shelves, which is causing drawdown on the inland ice, on the grounded ice upstream. Most of that is being caused because of changes in ocean heat flux underneath the ice shelves, which is causing them to thin. And then consequently, the buttressing force is being lost against the grounded ice, and the grounded ice is then flowing faster into the ocean and causing sea level rise. In Greenland, we're seeing different signatures. Again, in the center of the ice sheet in the plateau, we're seeing increased accumulation, so there is a slight increase in mass in the center, but the overall signal for Greenland is one of thinning, and that is being caused by ocean and atmospheric signals acting all around the edges of Greenland.
So we're seeing 200 gigatons per year of ice flowing into the oceans, which is enough to raise sea level by about 2/3 of a millimeter per year.
Combine that with the almost 118 gigatons lost in Antarctica, and sea level has risen a total of 14 millimeters over the 16-year period due to ice sheet melt. It may seem small, but the small changes add up.
What we expect by the end of the century is, on the order of 2, 3, maybe 4 feet of sea level rise. And because we have all of our infrastructure that is built around the coasts, we have a lot of vulnerability to a meter change in sea level rise.
The potential impact from sea level rise is one critical motivation for the continued study of the mechanics driving the changes in the ice sheets.
If we can understand those mechanisms and how they've played out over the last 30 years, well, then we can start to look and think about how will those ice sheets respond to what we project the climate to be into the future.
That is just incredible. It sounds like with these tools, scientists are able to be more confident that the changes we're seeing in the ice have to do with the long-term changes in the climate. Let's learn some more about that science. I'm joined by Ben Smith, lead author of the ICESat-2 study. Ben, can you take us through these results we just learned?
So we are making a first set of measurements with ICESat-2, and what's exciting about these is that they continue a set of measurements that were first taken in mostly the early 2000s. So those measurements were done with ICESat-1. They were laser altimetry measurements of both ice sheets. And the differences between those two let us see how the ice is changing over the 16-year period between the start of the ICESat-1 mission and the beginning of the ICESat-2 mission. So with those measurements, we can see a lot of sort of exciting things. We can see around the edges of Greenland and the edges of parts of Antarctica that the ice is thinning very quickly. There are areas where the ice sheet surface is dropping by more than several meters per year, so tens of feet per year. As you go farther inland from there, you see less and less thinning in general, until in the very interior of the ice sheets, we actually see small amounts of thickening. So what this means to us is that there are rapid thinning processes that are happening in association with changes that are happening in the ocean and the climate. And those are affecting the low elevation parts of the ice sheet that are close to the ocean. Farther inland, there's more snow falling than can be taken away by ice flow. And so the ice sheet is thickening a little bit. The mission also lets us add up those differences. So we can add up how much thickening we see and how much thinning we see. And we find that the thickening is, at this point, very, very small compared to the thinning that we see. So the rapid thinning that we see around the coast dominates the thickening that we see in the interior. And so both ice sheets are losing quite a bit of mass.
And why are these results so significant?
So this is kind of a definitive study. So we're making laser altimetry measurements. We know that these measurements are measuring exactly the surface of the snow. We have very high precision, so we can measure at the sort of inch level how much the ice sheet has changed. And we have a long time period, so we have a 16-year time period. So it's not just that we had a snowy year 1 year, or we just had a little bit of extra melt 1 year. We're seeing processes that have been going on consistently for a long time, and we can see the effect of that added up over a number of years.
And why is the ice melting?
So we're seeing two different effects here in combination with one another. We measured the net effect of these two things. We're seeing around the edge of Antarctica and the edge of Greenland that the ocean is warmer, and that's melting ice directly. So the ice shelves around Antarctica, which are floating ice, are thinning quite a bit, and the ice at the downstream ends of the outlet glaciers in Greenland are melting quite a bit. That lets the ice flow faster because there's less resistance to its flow. And so as the ice flows faster, the glaciers go faster, and ice can flow from the ice sheets into the ocean more quickly. So at the same time, in Greenland, we're also seeing the effects of surface melt. So the weather has gotten warmer in Greenland by quite a bit, and a lot larger part of the ice sheet is melting. And it's melting more every summer. So We're seeing surface melt and faster ice flow in Greenland, and we're seeing faster ice flow and ice shelf melt in Antarctica.
Thank you. So I think we have a time for one question from social media. A question from Tumblr is, how do you guys help with climate change?
So we are observing the effects of climate change. We are presenting the fact that we're seeing these changes, and we're showing that they are pretty significant. What actually helps is what people do in response to this. So when people see that we've produced about 14 millimeters of sea level rise between these two missions, we might think about what we need to do in response to that.
Well, thank you so much for joining us today, Ben, and walking us through these amazing science results on Earth's ice. For those of you just joining us, we're learning about just released findings about Earth's ice. One of the things we've heard our experts mention a few times is sea level rise. I'm joined by Dr. Helen Fricker, glaciologist, who is going to give us a better idea of how sea level rise works. Helen, thank you for joining us.
You're welcome. Thank you for having me.
So I understand it's not just warmer air temperatures that are melting ice, but warmer ocean temperatures as well. How does the ocean have an impact on Antarctic ice?
That's right. So all around the edges of Antarctica, there are parts of the ice sheet that reach the ocean. And in these places, we have very large areas of thick ice that's floating on top of the ocean. We call these ice shelves. Now, some of these ice shelves are so big that they're the size of Texas or France. Some of them are much smaller. But what they do is they hold back the ice, the grounded ice, that's sitting on the main part of the continent. And so it's kind of like a buffer region where if this ice shelf wasn't there, the ice would flow much faster into the ocean. You could think of them like a buttress, an architectural buttress, sitting there holding the grounded ice back onto the ice sheet.
So when ice that's already floating melts, how does that raise sea levels?
Right, so the ice that's floating, the ice shelves, when it melts, it doesn't raise sea levels straight away because that ice is already floating. You can think of it a bit like your glass of water. I have a demonstration here. This is a glass which happens to have Antarctica on it. If I put ice cubes in the glass, if you watch the level of the water, it will go up. This is because I'm adding more ice to my glass. And so the level has gone up above. So now you can't see Antarctica anymore. But if this ice melts, then the level of the liquid in the glass stays the same. And this is like an ice shelf. When an ice shelf melts, the level stays the same. However, what it's doing is it's reducing this buttressing force that I just talked about that the ice shelves play in the ice sheet. And if you reduce that buttressing force and if the ice shelf becomes thinner, its buttressing force is less, and the grounded ice behind it will be added to the ocean. And that's just like the ice that I added to the glass.
That's a great demonstration. So what is it that made you want to study ice?
I wanted to study ice, and in particular Antarctica, when I started my PhD. I just found it so fascinating to think about this, first of all, this continent at the bottom of the Earth that's so far away from everywhere else, but it's so important to us all. This interconnection of the entire Earth system with these different forcings, the atmosphere, the ocean, and just also the thrill of Antarctic exploration. And then later in my career, I've also got interested in Greenland, the ice sheet in the northern hemisphere, very similar processes acting there, but in different amounts. So together, all of the ice sheets are just so fascinating to me. I mean, I think we sit here in, at home at the moment, but in our, inhabited places that we live, and we don't really think that these continents that are so far away are going to affect us, but actually they do, because sea level is going to affect many, many people all around the world.
Yeah, thank you so much for explaining that to us, Helen, and it really helped me grasp the concept of how sea level rise works and how all of these things are interconnected. Thank you so much for joining us.
Oh, you're welcome.
So another way to understand sea level rise is to go into some of the communities that are being impacted by rising waters. Recently, our team visited the city of Norfolk and the Virginia Institute of Marine Science to see how the Hampton Roads region is responding to sea level rise and the effects of climate change. Let's take a look.
Sea level rise is a measurable difference in water level over time, and directly contributing to that is, of course, climate change. So as the temperatures rise, polar ice caps melt, and slowly the water level rises all throughout the globe. And there are localized impacts of sea level rise.
In Hampton Roads, we are particularly vulnerable to coastal flooding.
The Hampton Roads region of Virginia is the second most heavily impacted region in the United States when we talk about sea level rise, after, of course, New Orleans.
We're standing here at the Hague, part of Norfolk, Virginia, which is in the mouth of the Chesapeake Bay in southeast Virginia. This area will see what we call blue sky flooding quite regularly, where there's no storm event. And so this water comes up over onto this side, water breaches the bulkhead, floods the area around it and the road behind me as well.
A lot of my research, the Virginia Institute of Marine Science, involves the development of physics-based hydrodynamic models. These models tell us where flooding is going to happen before it does, when, and for how long. But you'll see all these individual structures here, most of them near the waterfront are inundated. The information provided by NASA satellites mostly allows us to validate the accuracy of our model in terms of telling us where the flooding actually happened from space.
The maps that come out of the models are really useful at showing the depth of water throughout the city at the street level so that we can, just make better data-driven decisions around the city.
These are two standard active remote sensors.
This is an example of a pressure transducer water sensor, and what we've been trying to do is compare data like NASA satellite imagery to see how it compares to the accuracy that we're getting at the street level. So when you put it all together, it's very valuable.
One of the main applications is really trying to see, before these events happen, where are going to be the problem areas in our communities.
Determine what roads need to be closed or intersections need to be closed when.
Where these projects should be permitted. Will this building last the 30-year life of a standard mortgage? Our models, as a representation of reality, have to be as accurate as possible. The additional information from the NASA satellites, Landsat, Aster, and MODIS, really helps us calibrate our model.
Having that regional water depth map really helps us in kind of understanding what the future day-to-day looks like in Norfolk with sea level rise.
And so better understanding sea level rise will help you decide places where you may wish to work or live in the near future. It also helps you better understand specifically what your risk is inherent not just with flooding, but also with the changes to our climate as our world continues to change, either for the better or worse.
That was an informative look at how communities in the Hampton Roads region are dealing with the impact of sea levels rising along their coast. Thank you to the City of Norfolk and the Virginia Institute of Marine Science for showing us how they use NASA data in these situations. Speaking of NASA data, we've talked a lot about how the new information gathered from ISAT-2 will help us. I bet you didn't know that in addition to the data gathered from space, we have researchers traveling into the field to conduct ground observations that validate what we're seeing from the vantage of space. Let's take a look at the footage taken from some of those field campaigns to get a sense for what it's like.
Hi there, I'm Thorsten Marcus from NASA and my colleague Brock, and we are here on Penny Bay doing ISAT-2 validation work on sea ice. I'm measuring sea ice thickness with an EM31
and I'm measuring snow depth with a magnet probe.
What you doing, Kelly? Closing up the GPS. Trying to breathe. Trying to breathe? What's the problem with your breathing? We're at 10,000 feet above sea level.
So it's really cool to be right next to one. You can see all the structure in the glacier. These glaciers form as snow from year after year packs on top and compresses down into ice. And so they provide a history of the climate as well as being really beautiful.
Wow, what an incredible perspective to see how researchers work in these extreme environments. It's really amazing. To tell us more about some of our own experiences working in Antarctica, I'm joined by Brooke Medley. Thank you for being here today.
Thank you for having me on.
So Brooke, you're the Deputy Project Scientist for Operation Icebridge. Could you explain where and why you go into the field to study ice? Why do you go into the field when we can just fly over it?
That's a really great question. So I've had the fortunate opportunity to be able to go to both Greenland twice last year and Antarctica as well. Most recently, Antarctica. I just got back a few months ago from Antarctica, where we actually were on the ground, on the ice, taking measurements both of surface elevation, which is what we see with ISAT-2, but also of other sort of measurements of how much snow there was on the ground, how thick is the ice, different sort of measurements that help us better interpret what we can see from satellite, from only just the satellite data. But while we were in the field in Antarctica, we had the unique opportunity of also being in the same location as Operation Icebridge, which is an airborne NASA mission. And so Operation Icebridge actually is a more than 10-year-long mission that was tasked to actually bridge the gap between ISAT, our original laser altimeter mission, and ISAT-2. It's this really amazing chance to have the high satellite in the sky measuring the Earth. Then we have our airborne campaign that has lots of different instruments, including one that is the same effectively as what ISAT-2 has on board. And then we're on the ground. So what that does is it really gives us the best picture of how the ice is changing, and we can then have the most confidence in our measurements because we see it at every single level.
So when you're out in the field, what does a normal day look like for you?
So when you're, say if you're on Operation Icebridge, which is the airborne campaign, we base typically not on the ice sheet for Antarctica. So we'll be based out of South America or Australia. And we do very long flights. So imagine you're on a plane for 12 hours a day, 5 days a week. So it can be very grueling and very difficult, but you get to see some of the most fantastic scenery I've ever been able to see. When you're on the ground, it's much different. So you're actually in the cold, trying to collect measurements and doing the best that you can, even though you're in huge gear, it's windy, and you just want to kind of crawl back inside and get warm again. So a little bit different perspectives, but at the end of the day, we're trying to answer the same science questions, which is, and complement one another as well.
That sounds incredible. What is it that made you decide to study ice?
That's a great question. So I never even really knew what a glacier was probably until I was in college. And I had never seen one, with my own eyes. And so I had the opportunity to move to Oregon after undergraduate. And when I did, I saw my first glacier. And I hate to sound cliche, but I absolutely fell in love. And so after that, I completely changed my career path to focus on research, and specifically research regarding glaciers and ice sheets. And I couldn't be happier. So.
Wow, what an experience. Thank you so much for joining us today and taking us into the field with you.
Absolutely, it was my pleasure.
And thank you for everyone watching at home as we explored Earth's icy regions and examined some of the latest science about how our planet is changing. You can continue learning about Earth and the ways NASA studies it by visiting nasa.gov/Earth or following @NASA Ice on Facebook and Twitter. See you next time.